go through the fundamental and interpretation of classical reservoir engineering using MS Excel. He will teach you how to analyze data effectively, utilize Excel tools to create insightful graphs and charts. This session promises to be highly practical and insightful, equipping you with the skills that you can directly apply in real world scenarios. Without further delay, I now invite Vinod sir to take over and begin this exciting session. Thank you, and over to you, sir. Vinod sir?
Yeah, thanks for the introduction, team.
Yes,
I can share my screen if, yeah.
now please try.
Okay, yeah, thank you. Okay, I hope everyone can see the screen. Can someone confirm?
Yes, it
Yes.
is visible.
Okay, yeah. So let's start the session on classical reservoir engineering, fundamentals and interpretation techniques using MS Excel. So Excel has been a powerful tool uh, during 1950s, 60s, 70s, 80s when there were no commercial softwares available to interpret data that is available from the field and to understand or get the future prediction, how the field is going to produce and how much can we recover and how to make money out of that. So Excel is quite uh, useful even now in the today's world, as many field professionals use Excel for their daily activities, especially in reservoir engineering. So classical reservoir engineering, as its name says, it's classical in nature. So whatever practices were being followed since the very beginning when the industry has started are classical RE methods. So in this, there are basically four methods. One is material balance analysis. The second is decline curve analysis. Third is pressure transit analysis, and fourth is reservoir simulation. So reservoir simulation, there are several simulators available, but we are going to use MS Excel to simulate the pressure and saturation distribution in the reservoir. And as an add-on, we also will look at production optimization techniques in the course. So the first topic for today would be material balance analysis. So to understand that, we need to just quickly run through oil recovery mechanisms or even gas recovery mechanisms like hydrocarbon recovery mechanisms. So each reservoir is composed of a unique combination of geometric form, geological rock properties, fluid characteristics, and primary dry mechanisms. So I hope there are many geologists and geophysicists in the call. So they'll be more enthusiastic in understanding the geology of the reservoir and how the understanding of geology helps us predict future performance of the reservoir and its production. Although no two reservoirs are identical in all aspects, they can be grouped according to the primary recovery mechanism by which they produce. It has been observed that each dry mechanism has certain typical performance characteristics and uh, limitations. Okay. So there are several characteristics like ultimate recovery factor, decline rate of pressure, gas oil ratio, and water production. So these four typically affect the economics and also production profiles of several fields. So primary recovery is either through natural flow or artificial lift. So in artificial lift, we try to give a pressure support in the wellbore. We don't apply in the reservoir. So whatever energy is there in the reservoir, we use that as an energy source during primary recovery. In secondary recovery, we try to maintain pressure in the reservoir by water flooding or gas injection. So we do water injection and gas injection to maintain pressure in the reservoir. Sometimes water flooding can also come in tertiary recovery because water flooding is like a piston displacement, where we try to use water as a tertiary fluid and push oil with this water. In tertiary recovery, we have thermal methods like steam, hot water, and combustion, in situ combustion, and gas injection like miscible CO2, immiscible CO2, hydrocarbon flue gas injection, nitrogen injection. And in chemical flooding, we have alkaline, surfactant, polymer, and of course, microbial and azole recovery. So these three mechanisms are quite critical because they will give us a recovery factor which is more than 20% if it is oil, or more than 50% if it is gas. The recovery of oil by any of the natural drive mechanisms is called primary recovery, and the term refers to production of hydrocarbons from a reservoir without the use of any process to supplement the natural energy of the reservoir. So there are six primary recovery mechanisms, or six driving mechanisms, which drive the fluid from reservoir till surface, which are rock and liquid expansion drive, depletion drive, gas cap drive, water drive, gravity drainage drive, and combination drive. So in rock and liquid expansion drive, generally what happens is rock is slightly compressible because of fluids in the reservoir within the pore spaces, and rock and liquid expansion. So water, connect water tries to expand a bit because it is incompressible anyway. Even then, due to some salt precipitation and some activities in chemical precipitation during production of oil and gas, there happens to be some expansion of rock and liquid. So this tries to drive the oil mobility or the oil movement towards the producing wells. In depletion drive, purely pressure depletion is the driving energy. In gas cap drive, whenever there's a primary gas cap already formed above the oil rim, so this tries to increase the pressure or apply the pressure on the oil rim, and it will try to help oil produce more. In water drive, the bottom water tries to give support to the reservoir or the oil rim, and will actuate the flow and will let the oil produce by supporting with pressure maintenance. And in gravity drainage drive, where gas, oil, and water, these three are segregated due to gravity differences. So when gas and water, when they both apply or provide pressure support, it is gravity drainage drive. And in combination drive, when there is rock and liquid expansion, depletion, gas cap, and water, that is a combination drive. So generally, combination drive has highest recovery factor, and water drive has the second highest recovery factor. So for people who don't understand recovery factor is the ratio of oil produced to oil in place. So we try to maximize recovery factor and also minimize the economics involved in maximizing this. So we choose several mechanisms in primary, secondary, and tertiary to maximize the recovery factor. So reservoir is a black box, and it is actually a black box, and whatever inputs we give is what outputs it gives us. So basically, material balance is followed with this principle that whatever volume is produced is the volume replaced. So as I'm talking about water drive, so what happens in water drive is when there is when there is some amount of oil produced, if I can just draw here, when there is some amount of oil produced, for example, say this is water, this is oil. So when there is some amount of oil produced towards the producer, some water encourages into the reservoir from the bottom. So whatever volume is produced is being replaced by water. That's what happening in material balance. So that volume produced will be oil replaced. So volume produced comes from gas production, oil production, and also water production from the reservoir itself. And volume replaced comes from volume expansion, water influx from the bottom water or edge water drive, and water or gas injection in secondary recovery to maintain pressure. So gas production, oil production, and water production sh produced should be replaced with oil expansion plus solution gas expansion. So what happens is, especially in undersaturated reservoirs, whenever the pressure is more than bubble point pressure, there is a lot of gas dissolved in oil as a single phase oil or black oil. So whenever the pressure drops below bubble point pressure, your gas starts expanding, and it forms a secondary gas cap. So solution gas expansion also happens in the reservoir itself when the pressure decline, especially in depletion drive mechanism, and also rock expansion plus water expansion, and initial gas cap expansion if there is primary gas cap available from day one of production. Of course, plus whatever we inject, water influx that is happening from the reservoir, from the bottom water supported aquifer, and whatever water we inject and whatever gas we inject. So whatever you're producing should be exactly equal to whatever is happening in the reservoir itself or whatever we are doing from surface. So if there is primary gas cap, gas available, and there is original oil plus dissolved gas at initial condition P is equal to Pi, this will exactly be equal to fluid production, be it oil, gas, or water, and gas cap volume change, release solution gas, oil volume change, net water expansion, rock expansion, and net water production. At a later condition, P less than Pi. Plus, if you are adding any more fluid, like water or gas injection, or if there is natural water influx happening in the reservoir from bottom water, these three should be equal to whatever is actually in the reservoir itself. So for people who are new to this connate water term, so connate water term is actually the saturation of water in the initial condition when P is equal to Pi. So this connate actually signifies in situ, in situation water that is available from day one or when the discovery has happened. So net change in oil and water production volume should be equal to gas cap volume change, release solution gas plus oil volume change, connate water expansion plus rock expansion. To go more into details, so net change in oil production will be NP into BO. So NP is the produced oil at surface times BO will convert this STB per day oil or STB volume oil to barrel volume oil in the reservoir condition. So BO technically has the units of reservoir barrel per stock tank barrel. So stock tank barrel is generally used for storage at surface. And net change in water production volume will be water produced times formation volume factor of water minus whatever water is influx naturally happening in the reservoir and whatever water we injected from surface. So we need to remove that. Gas cap volume change will be gas in place minus gas produced plus whatever gas you've injected times Bg, which is solution gas factor or gas volume formation volume factor minus whatever gas is in place. That is the gas volume change because gas generally expands in the reservoir, and we always track the gas volume change as a subtraction of what is produced from what is initial minus what is initial. Solution gas placed into the gas cap, which will be NRSI, where N is the oil in place, into RSI. So this is a new term. RSI is the solution dissolved gas oil ratio or solution gas oil ratio at the initial condition minus N minus NP is the produced and the remaining oil times RS, the current in situ gas to oil ratio into BG, which is the gas formation volume factor. So whatever is in place minus whatever is remaining should be the released gas, solution gas. So, and next is oil volume change, which is NBO at the initial condition, which is BO minus NBOI. So whatever in place volume is available times BO at the current pressure because pressure declines and BO increases. And NBOI is the initial BOI at the initial condition of the reservoir, the oil formation volume factor at initial reservoir pressure. There is something called as M, which is original gas cap volume by original oil zone volume. If there is primary gas cap available in the reservoir, we will try to also plug in M to understand what is the actual in place. We want to convert this gas volume to oil equivalent volume. So we will all sometimes call as OEG, oil equivalent gas, which incorporates M factor or which converts gas volume to oil volume. So reduction in hydrocarbon pore volume due to, of course, connate water expansion and rock expansion is given by VP is hydrocarbon pore volume by 1 minus HWI, which is NBOI plus NMBOI, which is 1 plus M into NBOI. As you have seen, 1 into NBOI is the oil volume plus MNBOI is the gas cap volume, equivalent gas cap volume that is converted to oil volume. So VP will now become 1 plus M into NBOI, which is hydrocarbon pore volume, by 1 minus HWI, which is oil saturation. This is nothing but SOI. So we convert pore volume into reservoir condition by dividing it with SOI, oil saturation. So pore volume expands or increases mathematically. And volume of water in the pore volume is 1 plus M into NBOI into the equivalent saturation of water in the initial condition by 1 minus SOI. So adding up all this, we get this entire equation, which is NPBO plus WPBW minus water injection, water influx minus water injection into water formation volume factor, which is in place oil minus whatever is actually there and whatever is produced, which is due to gas expansion, plus NRSA minus RS plus NPRSBG plus N minus NBOI minus NBO minus NBOI plus rock and liquid expansion. So when I club all this, we'll get this entire equation. So let's look at all these terms. So this term has three terms, 1, 2, and 3. So each term has its own significance. So the left-hand side term, which is NPBO plus RP minus RS into BG plus WPBW will be total cumulative production from the reservoir, which is oil plus gas that is released or primary gas cap gas plus water is equal to EO, which is BO minus BOI plus RSA minus RS into BG, EFW, which is 1 plus MBOI into CF plus CWSW by 1 minus SW times delta P. is EFW plus EG is BOI into BG by BGI minus 1. So MEG. This total term will be the total expansion that is happening in the reservoir because of pressure depletion, plus water aquifer influx is WE, that is happening naturally because of voidage being created in the reservoir, plus WIBW, which is water injection that we are doing from surface, plus GIBG is gas injection. So if we can also do modeling in advanced software. Current metal balance software available in the industry that is being used by everyone is MBAL from IPM, which is Integrated Petroleum Modeling, Production Modeling or Petroleum Modeling. Yeah. So in IPM we can try to understand among these four terms: one, two, three, and of course water influx. So which among these four terms is giving more recovery? So if you see, the total blue line is water influx, and green area is pore volume compressibility, yellow area is gas cap expansion, and red area is fluid expansion. So these four are the drive mechanisms that the software or also we can understand, when we try to analyze this in Excel. That is what we'll do today. We will understand whether the reservoir is being supported by any external drive mechanism that is naturally happening in the reservoir. For strong water drive, the recovery factor is supported or dominant of water influx. For combination drive, all of them support equally. For segregation drive, gas cap expansion support will give us, will help in more recovery. And combined segregation moderate water drive, all are equal, all are generally equal, but the less volume that is being recovered is due to fluid expansion happening in the reservoir, that is solution gas expansion. And coming to gas reservoir metal balance equation, gas reservoirs, generally gas are not ideal, they are real. So we consider Z factor as a potential term when we evaluate pressure. Now it is P by Z, which is Pi by Zi minus Pi by Zi into Gp by G. So when we collate all of them, we get P by Z is equal to Pi by Zi minus Gp by G into Pi by Zi. So more common forms of gas MBE generally are in high pressure reservoirs and medium to low pressure reservoirs, where in high pressure reservoirs, gas compressibility is much smaller and the effective compressibility term cannot be ignored. But in medium to low pressure reservoirs, effective compressibility is small compared to compressibility of gas, because gas is highly compressible, especially in medium to low pressure reservoirs. So when I plot P by Z versus GP, the gas produced, I get a straight line. If it is a straight line, and I can extrapolate that to 0 P by Z, which will give me initial gas in place. And if this curve, for example, goes like this, it has a zero slope, for example. So it means there is external support that this gas reservoir is having, which is generally water support that we estimate as reservoir engineers. So we will also look at one example today on P by Z plot for gas reservoirs. So gas reservoir MBE, as I've told you, assumption says that it is a tank model or zero-dimensional solution. It has uniform properties and it has instantaneous and uniform pressure distribution. So if it is straight line, it is depletion behavior or pure volumetric behavior, where pressure is the only force or energy that is being supplied to the reservoir to produce gas. But if it is going upwards with a zero slope, partly zero slope at a later times, so this can be water drive or gas injection effect. So pitfalls especially in low permeability reservoirs, when the permeability is so low, we can't estimate the gas in place. So gas in place will be huge in low permeability reservoirs because pressure depletion is so low, and this low pressure depletion will try to give us a near to water drive type of behavior. That is wrong. And also in thick reservoirs with PVT variations, it is not possible to understand what is the actual in place of gas. And also in gas condensates and volatile oils, where gas condensate will try to drop out in the reservoir at pressure below dew point pressure. That is also not possible to understand in gas reservoirs. There are some pitfalls. So coming to the straight line equation of MBE, so Haviland and Ode are two scientists which have developed this equation. They have converted the entire complex metal balance equation to straight line. So in straight line equation, the significance of straight line approach is that the sequence of plotting is important. And if the plotted data derives from the straight line, there is some reason for it. So we can estimate N or oil in place, water influx, whatever water influx is happening, size of gas cap, that is M, and what is the driving mechanism. So generally there are three applicable cases. In my career also I have seen three cases and generally happening in almost all reservoirs. We can estimate N in volumetric undersaturated reservoirs. We can estimate N and M in gas capped reservoirs. We can estimate N and WE, water influx, in water drive reservoirs. Let's look at these three cases. So case one, where I have shown you F underground withdrawal is N into EO plus MEG plus EFW plus WE. If I try to ignore, for example, EG, if I understand that there is no initial gas cap available, there is no primary gas cap, so RS is equal to RSI is equal to RP. Whatever solution gas oil ratio I have now is equal to solution gas oil ratio that is initially available in the reservoir at initial condition is equal to produced gas oil ratio. So F will now be N into EO plus EFW. Since we are talking about volumetric undersaturated oil reservoirs, we neglect WE. So if I try to plot F versus EO plus EFW, I get N as a slope. So let's look at slope. So if I plot, of course, say F by EO plus EFW versus cumulative oil NP or time, or if I just plot F versus EO plus EFW, I should get a straight line with a slope N. But this plot is called as Campbell plot. So Campbell is a scientist. So there are this plot where F by EO plus EFW versus NP or time will give me a straight line, horizontal straight line, which shows a volumetric system, which is purely due to pressure depletion. And if it is having a positive slope upwards or a constant slope later on, which suggests strong water drive, or if it has a positive slope and again it goes to negative, it's a moderate water drive. And if it has a positive slope in the initial days and again it goes to negative slope in the initial days itself, it is weak water drive. So we will also understand whether the reservoir that we are looking at has support or not. Second case, or case 3, which is gas cap drive reservoirs, if we look at F is equal to N into EO plus MEG, for simplicity we neglect W is equal to 0, we make it 0. The effect of water in pore compressibilities can be considered negligible. So yeah, in this N and M are unknown. So a plot of F versus EO plus MEG on a Cartesian scale would produce a straight line through its origin with slope of N. Yeah, F versus EO plus MEG will give me a slope of N. But if I don't know M and I know N, if I don't know the size of gas cap, which is derived from M, which is gas cap gas by oil volume, and if I know N in place oil, so I can rearrange the equation F is equal to N into EO plus MEG to F by N minus EO is equal to MEG. So this is now Y is equal to M into X. So if I plot Y versus X, I get a slope M. So I can estimate what is my M initially. From that I can estimate the gas cap gas. And next is if I don't know both of them, so I can rearrange the equation as F by EO is equal to N plus Mn EO EG by EO. A plot of F by EO versus EG by EO, Y is equal to C plus Mx. So F by EO versus EG by EO will give me an intercept N and a slope Mn. From this intercept N, I can calculate M, small m. This is a very good approach of estimating N and M together. And case 4 is water drive reservoirs. So if I have F is equal to N into EO plus MEG plus EFW plus WE. For simplicity, I'm like neglecting EG because I try to predict that there is no gas cap support available. There is purely water support. And if there is strong water drive in the reservoir, we also can neglect EFW because they are very weak as compared to WE effect. So F will be N into EO plus WE. If I try to rearrange this equation as F by EO is equal to N plus W by EO. If I try to plot F by EO versus W by EO, I get a slope 1 and intercept N. So I'll get a plot like this. Slope 1 and intercept N. So this N will be my in-place oil in place. So these three cases are quite critical or helpful in estimating N value, that is analytically estimated. Also in water reservoirs, when we want to estimate what is the supporting water drive with models. So pot aquifer model is one good model, which is for finite aquifers or small aquifers, where we estimate WE as sum of compressibilities of water and formation times water influx or water initial volume of water in the aquifer times F, which is the encroachment angle, into delta P due to water influx, Pi minus P. So Wi is pi into Ra square minus Ra square H5. For example, if I take a reservoir like this with an angle theta, fractional angle or encroachment angle, and I have a aquifer that is coming from the edge. So this is what I'm estimating Wi, which is pi into this is Re, the radius of external radius of water, and Rw, Ra, aquifer radius. So pi into Ra square minus Ra square into H into phi will give me the volume of water, initial volume of water in the aquifer by 5.615 will give me it in barrel because everything is in feet cube. From this, I can calculate what is my actual water influx that's happening from the reservoir for a drop of pressure Pi minus P. Pi is initial pressure minus P is the current pressure. So if you plot F by EO versus delta P by EO, I'll get a straight line technically with a slope K and intercept N. So K is this one, CF plus CW into WI into F, and N is the in-place volume. So this is how we use material balance equation as a good analytical technique to estimate in-place volumes and also estimate what is the gas gap volume that is available at the primary condition, and also we can understand how much recovery factor is possible for this reservoir. So the MB is valuable analytical tool for evaluation of reservoir dry mechanisms. Even though it is zero dimensional, it offers tools for gaining diagnostic insights. So I think someone might be having question why it is called a zero dimensional. So zero dimensional means the metal balance equation has or is dependent on a pressure P bar, which is averaged out in the reservoir. So we assume that the pressure is same across all the portions of the reservoir, right from the reservoir external radius to the wellbore radius. So that is why no parameter has any dimension in metal balance equation. We assume that it is purely homogeneous system and every parameter is averaged out in the entire reservoir. For example, in water drive reservoirs, there is porosity term phi. So phi is constant value across all parts of the reservoir, but that is not possible practically. We might have some tight areas where the porosity is less. Some mineral deposits happen somewhere due to depositional sequences, and that is all ruled out in metal balance equation. So MBE applications, we have software also available. The most rigorous method for reservoir evaluation and analysis is reservoir modeling, which is in conjunction with metal balance equation or an analysis. If the reservoir engineer is unsure of the reservoir dry mechanisms, it is advisable to start the process of analyzing the performance of the reservoir with metal balance methods and later advanced reservoir modeling as more knowledge of the reservoir dry mechanisms is gained. In practice, material balance can be of assistance to in determining type of reservoir model to construct and assessing the quality of reservoir performance data to use in conducting reservoir modeling. That's all about metal balance equation. If you have any doubts, just let me know. Okay, I'll try to reduce my speed. Well noted. Yeah. If there are no questions, let me just go forward. Okay. So next technique in classical reservoir engineering is decline curve analysis. So production decline analysis or decline curve analysis is a traditional means of identifying well production problems and predicting the well performance and the life based on real production data. That is quite important in decline curve analysis. It's an important tool that assists production monitoring and forecasting for effective reservoir management. DC models are developed to obtain more accurate estimate of the reservoir when sufficient production history is available. So material balance is, such a tool or such a technique which is not that dependent on sufficient production history availability. But for decline curve analysis, we need sufficient production history to be available. The predictions of by DCA usually becomes more accurate as more data is compiled through the time. So the basic equation for performing analysis with decline curves or decline curves is ARPS equation. So ARPS equation is technically 1 by Q, dQ by dt is minus BQ power D, where Q is technically the oil production rate, B is the decline rate, and D is the decline constant. So if the value of D is 0, it's exponential decline. If the value is between 0 and 1, it is hyperbolic decline. And if the value is exactly 1, it is harmonic decline. So for each of these decline models, we have the rates that are derived, where for exponential decline, D is equal to 0, Q is equal to Qy e power minus Bt with the decline rate B. And B can be estimated from ln Q1 by Q2. Q1 can be the rate at any time T1, and Q2 can be the rate at any time T2 after T1. So ln Q1 by Q2 by T2 minus T1 will give us B, and the produced cumulative production that can happen is 1 by B Qi minus Q. So we'll plug in a value of Q. Example, say whatever economics we have. Let's say a field is available, a field is in my hand, and that is producing currently 10,000 barrel of oil per day, and I can just assume that 50 barrel of oil per day is the economic limit of this field. So I know my B, and I assume that it is declining exponentially. I'll plug in Qi 10,000 minus 50 by whatever B is available per month, per year, per day, whatever it is. So I'll get NP up to the abandonment rate. That is how decline curve analysis works. We can estimate how much more we can produce above what we have produced till now. So if I draw a plot of rate and time, I'll get these three curves where the first top curve represents constant percentage decline or exponential decline. The bottom curve represents harmonic decline. So if you see, all the three cases have the final rates Q as same, but the decline is a bit faster in 3 in harmonic, but it is a bit slower in 1 exponential. That is how we try to see which curve fits our actual production decline that is happening in the field. Based on that, we choose a particular decline model. We have another method called de Jong's model. So this model is used especially to model data in unconventional wells where the flow remains in the transient flow regime for long periods of time. So can anyone just tell me why is the flow remaining in transient flow regime? And of course, what is transient flow regime? If anyone can tell me, I'll be more than happy. You can also write in the chat box if you're unable to talk. I'm okay. Yeah, someone, Shubham Gupta, answered dP by dt is not constant in transient flow regime. We cannot say that dP by dt is not constant, but we can say that at the reservoir boundary, the pressure keeps on increasing. We cannot estimate where is the boundary in transient flow regime. So transient flow regime has two conditions. At R is equal to RE, when the radius reaches reservoir extent radius, P will still be increasing. The pressure will still be increasing. So the boundary is not felt in transient flow regime. Yes, you're right. In unconventional reservoir, permeability is very low and it takes so much time to reach the boundary, flow boundary. So for those reservoirs, we use this model or de Jong's model, because to model that reservoirs with low permeability, it is very tough with a traditional APT model. So in this model, we took linear flow equations for rate and cumulative gas and modifying them with a correlation developed with real data matching, giving two new equations of flow rate for flow and rate. So the flow rate is Q is equal to Q1, which is de Jong model parameter determined graphically from historical data and other model parameters, and T is time, e to the power a by 1 minus m into t power 1 minus m by minus 1, where m and a are again de Jong model parameters and t is time. The next method model we have is there is another equation for cumulative gas production, which is Q1T of AM by AT minus M. Next is PLE model or power law exponential model, which was introduced in 2008 to overcome the overestimation due to application of ARPS method in low permeability reservoirs. This model was developed to provide a better estimate for the future production rates when the past production includes data from both the transient and boundary dominated periods. So can someone tell me what is another name for boundary dominated periods? Anyone? We call boundary dominated flow with another name generally yeah. Shubham Gupta is right. It is semi-steady state or pseudo-steady state. Sorry. Yeah, pseudo-steady state or semi-steady state. And unsteady state is transient flow regime. Semi-steady state or pseudo-steady state is boundary dominated period, and steady state is when the boundary is felt and there is no more extent beyond that point. So it is a good candidate for application in unconventional formations where Q is equal to QO e to the power minus d infinity t minus d1 by n t power n, where QO is the initial rate, d is Arb's decline constant, that is B again, d infinity is the loss ratio at t is equal to infinity, d1 is the loss ratio at t is equal to 1, and n is time exponent. The next or last model is stretched exponential decline model. It was based on fitting the past production data dominated by the transient flow regimes. So Q is equal to QO exponential minus T by tau power n, where tau is characteristic time constant and is exponent. So we can estimate GP, the cumulative gas produced. So limitations is that decline curve equations assume that production decline is proportional to the reservoir pressure decline. So if you look at exponential decline, for example, the exponential decline rate is constant all over the entire time period. But that generally won't happen in some reservoirs where there is extensive water loading happening, because water loading hampers production rate. In addition, conventional DCA assumes that constant flowing bottom pressure, drainage area is constant, permeability is constant, skin is constant, and existence of boundary dominated flow, which is not technically possible every time in every reservoir. It is pure mathematical analysis and doesn't take into account the operational constraints. These could be bean size increase or decrease, artificial lift systems, etc. So bean size is generally the choke size. So anyone in the audience have experience with choke, like uh, choke operation, who are from production teams or drilling teams? You can raise your hands. It will be a good boost to all the audience. Okay. Uh, So let's now quickly go into Excel exercises. I can see someone asked, please can we have field data to use it with MS Excel? So let me quickly go to a metal balance study in Excel. So I hope everyone can see the screen.
Yes.
Okay. So this is an example. The Virginia Hills Beaver Hill Lake Field is a volumetric undersaturated reservoir. So the calculation indicate that reservoir contains in place 270.6 million stock tank barrel of oil in place. The initial reservoir pressure is 3685 psi. The following additional data available, where we have SWI or connect water saturation 24%, formation water compressibility, water formation volume factor, and bubble point pressure 1500 psi. So we have pressure decline that you can see here, number of producing wells available, BO at every pressure, the oil formation volume factor, and the produced oil and water production. So NP and WP are cumulative terms. So I have taken them down in Excel. So let's quickly plot reservoir pressure and BO. So I have told you that when pressure declines, BO increases. So let's see, is that happening or not? So you can see very well. So when the pressure is declining from right to left, your BO is increasing. So this increase in BO is due to the expansion of isolation gas that will try to increase the volume of oil. So BO is nothing but the ratio of volume of oil at reservoir condition by volume of oil at stock tank condition. So you can see it's very beautiful that BO is increasing as pressure is declining. But this happens only up to bubble point pressure. Once it is reached, it will decline again because gas is now released out of oil as P is now less than bubble point pressure, where the first gas bubble has expanded from oil. So let's quickly try to use the techniques we have understood in material balance, where we will try to first calculate underground withdrawal. So F would be, which is underground withdrawal. So this should be technically, we need to take them down to reservoir conditions. So NP star BO. So STB is now converted to barrel, reservoir barrel, plus WP star water formational factor, because that is being produced from the reservoir. Okay. So it is now 0. And if I just fix F3 and B7, I need to fix them because they're F3 is not constant, it's changing with pressure, but B7 is constant. Let me add a dollar sign, and yeah, let me just drag them. So I get these as my underground withdrawals. So this is G15 times F15 plus WP into BW. Yeah. So let me put this format for this also. Yeah. So, and let me try to bring them with only 2 decimals. So now I got F and other parameters. So now the prime importance is, let me just share the screen again so that you'll get clarity. Okay, I check the screen only. So if you see, we need to plot F by EO plus EFW versus NP, or we can also plot F versus EO plus MEG or EFW. Since we don't have EFW and M and EG, we only plot F versus EO, where EO is nothing but, can someone tell me what can be EO? Anyone? What could be EO? Expansion of oil term. EO. What is that? How can we track the expansion of oil? Okay, someone asked a question on what principle is the evaluation of volume of a tank based on metal balance? What are the steps to follow and how are the equations used? So tank based approach is that which assumes that the in place volume, which is either filled with oil, water, or gas, is nothing but area times height times porosity. So whatever pore volume is available is assumed that it is filled with oil, water, or gas. So that is the principle how we evaluate volume of a tank based on metal balance. And the steps we are following is what I'm showing you to you right now. We will try to just understand that whatever is produced is that is actually being replaced by something else from the top or from the bottom. That is how we balance everything. So whatever volume goes in, whatever volume comes out, if some volume that is going in is left over in the reservoir, it is accumulating in the reservoir. So volume in minus volume out will be volume accumulated. This actually comes from mass in minus mass out is accumulation. So we convert mass to volume using density of oil. If it is incompressible, we can directly put density. But if it is compressible like gas, we cannot use density. So oil and gas, oil is slightly compressible, gas is highly compressible, and water is incompressible. That is how we derive from mass balance to metal balance. Okay, so someone answered that we can calculate EO using RS. No, that is not the way we calculate EO. We calculate EO using BO and BOI, the formation volume factors, because EO is nothing but the expansion of oil that is happening in the reservoir. Let me just take you back. So if you can see BO minus BOI plus RSA minus RS into PG, this is nothing but EO, where we don't have initial gas cap because the pressures that you see in this uh, data given is above bubble point pressure. There is no free gas cap available in the reservoir. So it is purely solution gas expansion. So it is nothing but EO can be calculated as BO minus BOI. So what is BO? This is current BO minus BOI. That is the initial BOI. So let me just click. It is 0. Let's fix BOI dollar sign. Yeah, let's drag it. Okay. So this is my EO term. I'll just put the same format. Okay. So I got this as EO. So I now just need to plot F versus EO. So let me insert a plot. Yeah, this is now my F versus EO plot. It's quite beautiful. Okay, I think there's a mistake. So let me insert it manually. So insert, plot, yeah, select data, add. So x-axis should be EO and y should be F, the underground withdrawal happening. Yeah, this will be my F versus EO plus EFW. Oh, sorry, F versus EO. So if I just try to put a trend line to this, maybe a linear trend line. So linear, and yeah, it is closely a straight line. So let me change the color into black. Okay, let me bring them down to just no decimal number, no decimal. So reservoir engineers are very perfect. They try to keep it perfect. So that is what I have practiced till now, and that's what I like to see in the plot. So it starts from 0 to 4000, and EO term starts from 0 to whatever max it is, 0.008. So I need to just look at the straight line equation. So I'll display equation on chart. So if you can see, slope is 49,944,9. So if this is nothing but F is million stock tank barrel, sorry, 1000 times stock tank barrel. So this is nothing but 4499449 million, sorry, MSTB. Let me just also copy this equation, control copy and paste it here. So this is my equation right now. Let me just put it in yellow, bold, and red. So if I divide this 499,449, 499,449 by 1000 should give me the stock tank barrel in million. So for 499.44 is the oil in place, MMSTP. So it's very huge. That is how we estimate the in place volume, as you can see. Apart from this, from modeling perspective, we can also plot the number of producing wells versus the total withdrawal. So in reservoir simulation, we have something called a screening curve where we see the benefit of additional wells that are being drilled. Is it really giving us more volume that is being produced? You can clearly see 4 wells at the pressure of 3664 psi is giving me 133.4, has given me 133.47 MSTB of total withdrawal. But suddenly, if the wells have increased by 15, I got 282, which is more than double. And if I increase the wells by 6 more, I got 478.23. So it can be a good exercise for all of us. So let me also add one more plot. So let me copy this again and I'll paste it here. And I need to just change the data. So I'll shift this. F is my y-axis. So F would be y-axis only, and X would be my number of producing wells. So yeah, I need to remove the straight line. So if you can see, there is a creaming curve given here. So let me change the title to creaming curve. So as I'm telling you again and again, creaming curve, the basis of creaming curve is such that we see the uh, you know positive effect of new wells that are being drilled. So creaming curve is giving me a increasing trend, and of course, when the wells have increased, it has increased by huge numbers. So that is what. If we just try to only look at oil, for example, let's not focus on water. Let's look at only oil. So even oil is giving me good slope in creaming curve. So this means that number of wells can be increased because we have produced only 3.4 million barrels, but we have 499.449 in place. Let's just divide this produced till date by 1000 and divide this with the in place volume to see the recovery factor. So recovery factor is just 6.8%. That is so less. So if I just put in percentage, it's not than 1%. It is less than 1%. That is very less as to consider in a field. So we need more number of wells to be drilled in this field. This is recovery factor, which is produced oil versus in place oil. That is how metal balance analysis is used with just production data and of course BO. We need to understand BO also. This is one example for oil reservoirs or unsaturated oil reservoirs, and we have one more example for gas reservoirs. Let me just show you that as well. Yeah. So in gas, as I have shown you that we generally rely on plot of P by Z and GP. So I have data of P by Z versus GP, cumulative gas produced. When I plotted P by Z versus GP, I get a straight line, with a constant slope, of course. And if I extend that or extrapolate that to the zero y-axis value, I get an x-intercept, which is my in-place gas. So this in-place gas is somewhat close to 14,000 to 15,000 mmscf. So if I take a mid value, maybe 14.5, so 14,500 mmscf is my in-place gas in this gas reservoir, mmscf. So if I try to find the recovery factor, so recovery factor should be whatever gas is produced cumulatively till date, which is this, by what is in the reservoir, 14,500, and that is in percentage. So you can see 74% is the recovery factor of this reservoir. So as I've told you, for oil reservoirs, we have a recovery factor of generally 20 to 30% only, but with primary recovery mechanism, of course, not secondary and tertiary. But in gas reservoirs, we get more than 50% recovery with primary drive mechanisms only. Similarly, we have two more zones. Zone 2. Zone 2 is giving me close to 11,000 MSCF in place gas, and Zone 3 is giving me approx 14,000 nearly in place gas. So we can find these three zones are nothing but three reservoirs in the same well. There are several wells in this field, and we have multi-zone completion where we have 2 to 3 cubics in the same well, and these wells are producing gas. So we have the data of P by Z and GP. So I can just estimate the recovery factor for this recovery factor. Just to show you how we use the concept of mineral balance analysis in Excel, how it used to be done before, and how even now it is being used. That is my main point. So that is what I wanted to show you. So I think the person who asked me to show field data in Excel, I think I have shown you. Okay, so let's get back to our presentation. So we'll now go to reservoir simulation. So this is also one other classical reservoir engineering approach. Currently, there are several softwares or simulators available to do this, but yeah, we can do it in Excel also. So simulation has several steps where we try to understand recovery process, and we formulate the recovery process with several equations, which comes out to be nonlinear partial differential equations. We discretize that to make it into algebraic equations. We represent wells and we linearize them. So wells are generally internal boundaries. So we linearize that to linear algebraic equations, and we have solution for these linear algebraic equations, which give us pressure and saturation distributions and well rates. So we validate and apply this to this is the entire simulation process. So formulation outlines the basic assumptions that are inherent to simulator, states these assumptions in precise mathematical terms, and applies them to a control volume in the reservoir. So control volume is the volume I have chosen to do simulation to understand how the flow is happening, what kind of flow is happening, and this flow, how it is affecting the pressure distribution and saturation of oil distribution. The result of this step is a set of coupled non-linear partial differential equations that describes the fluid flow through porous media. Next, discretization is the process of converting PDEs into algebraic equations. So the partial differential equations will now be converted into algebraic equations. So we have numerical methods to do that. This discretization process results in a system of nonlinear algebraic equations. So what we do is we divide the entire reservoir into small blocks. So we discretize the entire reservoir and populate the reservoir properties into the different blocks that we have chosen. So if suppose say permeability is currently constant in the entire reservoir, we make it constant to all the grid blocks we have chosen in this process of discretization. The choice of choosing a grid size is always in the geologist's hand, because he knows how the geology is varying in the reservoir, and he can populate those properties like porosity, permeability, and vertical and horizontal permeability and other rock properties, in each of these grid cells. Then we linearize them, which involves approximating nonlinear terms like transmissibility, production rates, and coefficients, etc. This linearization results in set of linear algebraic equations. So we validate the reservoir simulator. Validation of reservoir simulator is the last step in developing a simulator, after which the simulator can be used for practical field applications. So we make sure that the number of errors are low. So we for discretization we have two types of grids. One is block centered grids and one is point centered grids. In block centered grids, grid blocks with known dimensions are superimposed over the reservoir. But in point centered grids, grid points are distributed over the reservoir before the block boundaries are defined. So some external boundaries like no flow boundary that comes from PTA, that is pressure transit analysis, where we try to understand where is my boundary. That is no flow boundary or a constant pressure boundary or a leaky boundary, whatever it is, or a fault. So dp by dx is equal to c at the boundary, where the transient has reached the boundary and it is felt by the reservoir, by the flow. So that means that it is a pseudo steady state or semi steady state condition. And internal boundary can be a fault between the grid cells. These are grid blocks. And also no reservoir block and also ceiling faults, where my transmissibility between these two grid blocks is zero. So transmissibility between this to this grid block is zero because there is no flow happening because there is a discontinuity between these two grid blocks. So we have an example for, don't worry, the entire material or the entire topics will be discussed in the actual course. So I also have beautiful course outline at the end of this webinar. So we encourage you to join the course. So example one, where we have 5 grid blocks in a one-dimensional flow process, and we have boundary that is felt, boundary available, which is dp by dx is 0. There is no pressure gradient beyond this one grid cell and after fifth grid cell. Delta x is delta y is equal to delta y, which is 1,000 feet, and delta z thickness is 75 feet. So liquid, water oil formation, water formation volume factor is 1, and also liquid means which is oil. Compressibility of that liquid, which is oil, is 3.5 times 10 power minus 6 psi inverse. Kx, the x direction permeability is 15 millirc. Porosity is 0.18, viscosity is 10 centipoise of oil, and BO is also at initial condition also 1. So we use time step size delta t is 10, 15, 30. For simplicity, we only want to look at 10 days now in this webinar. So we want to determine the pressure distribution during the first year of production. So the equation that I formulated, we will calculate the transmissibility between all the grid blocks, which is beta c ax kx by mu l bl delta x, where beta c is the constant, which is 1.127 times ax x direction area, which is 75,000 into 1,000 times 75, the flow area available, the cross sectional area available, which is 1,000 times 75 times kx, which is 50 millidarcy or 0.015 darcy by 10 viscosity. Bl is 1 into 1,000 is x direction thickness, which is 0.1268. So it is now constant in all the grid blocks between 1 and 2, 2 and 3, 3 and 4, and 4 and 5. But after 5 and before 1, there is no transmissibility available because it is a no flow boundary. So for grid block 1, time step 1, Pi is 6,000 psia. So if you can see, we have a well producing in grid block 4 with 150 STP per day. So negative sign like shows that it is being pulled out from the reservoir, like a material balance. So whatever is being produced is the void is created in the reservoir. So P1 is 6,000 psi, P2 is same, the initial condition, but P3 is 6,000. But you can say P4. P4 at the next time step is 5821.75 psi. So the pressure has dropped because the well is producing in grid block 4. And P5 is again 6,000. So in this, the number of days used, delta T is 10 days. You can see delta T is 10 days. So after 10 days, we get a pressure of 5821.75 psi in grid block 4. But next, if you look at time step 2, for the next 10 days, we also can see a decline in pressure in grid block 3 and grid block 5. And see that they both are equal because it is homogeneous reservoir and pressure drop is constant or significant in both the grid blocks, which are in contact with the existing grid block, which is producing oil. So 573.14 is same in grid block 3 and grid block 5. These grid blocks 3 and 5. So we have this as distribution of pressure after 10, 20, 30, 40, up to 1 year. Let's now look at this example in Excel. Yeah. This is the example that I wanted to show you, the same example where initial pressure is 6,000 psi, BL is 1, CL compressibility is 3.5 10 power minus 6 psi inverse, KX is 0.015 RC, porosity 0.18, 18% porosity. So we have alpha C and beta C, two constants, where alpha C is that converts feet cube barrel to feet cube 5.615, and beta C is the conversion factor that came in Darcy's law 1.127. So we have two terms. C1 term is the transmissibility term, is 1.884, and C2 term is C1 is this beta Cx kx by mu l bl delta x, which is 0.1268, and C2 term is this term on the right hand side, 1.1884. So this is the equation that we use to calculate the pressure at next time step. So if you can see, there are some formulas given here. So the same equation that we're using for explicit calculation, this equation. So in for grid block 1, so Txl minus 1, you can see here there is Tlx 1 I plus 1 by 2 and Tlx I minus 1 by 2. Since this is the block center grid, so we have a transmissibility term on the grid phase. So for grid block 1, there is no Tlx I minus 1 by 2, the previous grid cell, zero grid cell. And of course, for grid block 5, we don't have the next grid block available to for flow to happen. So after 10 days, it is 5821.75 psi in grid block 4, since the well is producing at a constant rate of 150. For example, if I just reduce this to say a large value, minus 150 will now, suppose say, will become minus 300. Just observe the pressure distribution, they change instantaneously. So when it is doubled, the reservoir pressure in the grid block 4 after time 10 days is now more, and when it is minus 150 it is less. Minus 150, the pressure is 5821 psi, 5821, and when it is minus 300 it is 5643, 5643. So the difference between these two, which is this minus this, it's around 178 psi. So to produce a rate of 150 barrel per day more, the reservoir pressure declines by 178 psi, and it reflects after 20 days in grid block 3 and grid block 5. And after the end of the 1 year time period, it is now 2114.81 psi in grid block 4, 4688.82 in grid block 1, because it is farthest from grid block 4, 3443.19 psi in grid block 3, 2650 in grid block 5, and 427 in grid block 2. That is how we can estimate the distribution of pressure in the reservoir using explicit solution. So this is how simulator works. The backend code of simulator is this. That is what we can do in Excel. So this exercise also will be done in Key. We will build this entire Excel sheet in the actual course. So let me just quickly go through the course content for your understanding. Okay, so day 1, we will talk about the introduction to reservoir engineering and pivot analysis, where reservoir engineering as a discipline for upstream oil and gas business operations is explained in detail. We will go more into fluid properties. We will discuss about BO, BW, BG, and RS. We will also look at some analysis of reservoir fluids in laboratory. We will also understand how to plot PVT properties and how to estimate them in MS Excel. And this can be as an inference to simulation studies. Day 2, we'll look at metal balance and reservoir performance calculations, where fundamentals will be dealt in detail with derivations, and we understand the definition and types of metal balance equations. We apply them to primary and secondary recovery scenarios. We do calculations for an oil reservoir, and we analyze injection data for pressure maintenance. Day 3, we look at decline curve analysis, where we will dive deep into exponential, hyperbolic, and harmonic decline models. We use Excel to model and forecast future production. We estimate the reservoir performance from production data. Day 4 is more into PTA, the well test interpretation, where we'll understand what are the objectives, the basic terminology and equations, types of pressure tests like build-up, drawdown, and flow after shut-in. we'll understand the bulk virgin reservoir models in middle time region, radial flow, bounded reservoir, wellbore storage. We use Excel to calculate parameters like permeability, skin factor, and drainage radius. So we have a detailed 1.5 hour webinar that I have lectured last time. So you can go through that webinar on especially well test interpretation in the YouTube channel of Advantage Learning. So day 5, we will look at production optimization, where we will try to link the reservoir to surface, where we will understand importance of production optimization. So we don't want to maximize or minimize. We want to optimize that. So that is maximizing recovery while minimizing costs. We will understand KPIs, key performance indicators like production rates, pressure profiles, and equipment efficiency. We also will look at optimization methods and tools like monitoring, analysis, and system improvements. We will also use MS Excel for node analysis to understand what are the bottlenecks in the entire process system and optimize entire production systems. That's all from my side. If you have any doubts, just let me know. I'll be happy to answer your questions. Okay, when is this course? So the team will let you know when we will start the course. But yeah, if you're interested, please register for the course and the team will get back to you. Any other query? Okay. Can I get the details of the course? I'm interested. The start date and fees. Yeah. Please talk to the team and team will let you know the start date and the fees for the course. Thanks for your interest primarily. I'm very happy. Yeah. Okay. I think I'm done. If there are no more questions, yeah, handing over to you, team.
Okay, sir. Thank you very much. I think all the questions are answered. Okay, thank you.
Yeah. Thank you.